Find somewhere comfortable. You don't need to follow any of this closely. You don't need to remember a single word. If your eyes are already closed, leave them there. If your body is already heavy, let it stay heavy. Tonight we're going somewhere very far away, so far that the distance itself becomes a kind of rest. Just let the words drift in, the way light drifts through a curtain, softly, without effort. If today was hard, and maybe it was, maybe it carried more than its share, then know that none of that has to come with you into this hour. Whatever you were holding, you can set it down here. The day is already behind you. It's already becoming something smaller, something quieter. You don't need to carry it any further tonight. We're going to travel, in a gentle sort of way, to one of the strangest objects in the universe. Something so dense, so extraordinary, so far beyond ordinary experience that even the scientists who study it spend their whole careers standing at the edge of what they understand, peering in. And yet, and this is the part I find quietly wonderful, it is made of the same basic particles that make up your hand, the pillow beneath your head, the walls of the room around you. The same particles pressed into a form so concentrated, so still in its own way, that it almost doesn't seem real. We're going to spend this hour with a neutron star. We'll get there slowly. We'll begin where all neutron stars begin, with a star that has been burning for millions of years and is finally, quietly letting go. And we'll travel inward from there, layer by layer, into something ancient and patient and almost impossibly small. You don't need to follow. You don't need to understand. Just let the words arrive and let them go again, like waves that come in and pull back without asking anything of you. We're in no hurry tonight. Somewhere in the universe, and I mean this literally, right now, as you lie there, a star is dying. Not in any way that would look violent from a distance, not at first. From far enough away it would simply look like a star, the way it has looked for millions of years. To understand what a neutron star is, we have to begin here, with the star that becomes one, not our sun. Our sun is far too small for this story. The stars we're talking about are much larger. Some are 8 times the mass of our sun, some are 20 times, some are larger still. They are among the brightest objects in any galaxy, pouring out light and heat at a rate so vast that they burn through their fuel in a few million years, which sounds like a long time until you realize our sun has been quietly burning for 4.5 billion years and has roughly the same again ahead of it. These massive stars live fast, and they die in a way that changes the surrounding universe. For all of its life, a massive star is held up by a kind of balance. Deep in its core, the temperature and pressure are so extreme that atoms are constantly being fused together. Lighter ones pressing into heavier ones, releasing enormous amounts of energy in the process. That energy pushes outward, and the star's own gravity pulls inward, and the two forces hold each other in a kind of deep, unhurried equilibrium. The star neither collapses nor flies apart. It simply burns, balanced between those two vast forces, the way a campfire holds its shape as long as there is wood to give. The fuel a star burns changes over time. It begins with the simplest, lightest material, hydrogen, the most common thing in the universe. Over millions of years, the hydrogen in the core is used up, fused into helium. Then the star begins fusing helium into carbon, then carbon into heavier things still. Each fuel lasts a shorter time than the last. The star moves through them the way a long journey moves through provisions. The early supplies are plentiful and slow to diminish, but as the journey goes on, what remains runs out faster. Eventually, the core is producing iron, and iron is where the journey ends. Not because the star runs out of iron, there is plenty of iron, but because iron is different. Every fuel the star has burned so far has given back more energy than it took to start the reaction. Iron does not do this. Fusing iron takes in energy rather than releasing it. The star cannot burn iron for warmth any more than you could heat a room by burning ash. The iron simply sits there, accumulating in the core, giving nothing back. And so the outward push begins to slow, then it slows further. The core, over a period of time that is both very long by human reckoning and very short by astronomical reckoning, builds up an iron heart at its center, a sphere of iron, perhaps the size of our Earth, dense and inert, held up only by the last of the star's waning pressure. Around it, the outer layers of the star are still burning, still fusing lighter elements, still pouring their energy inward. But the core is no longer answering. There is something quietly moving about this image, if you let it arrive softly. A star that has spent millions of years in perfect balance, giving out light and heat across unimaginable distances, finally reaching the point where there is simply nothing left to give. The campfire has burned so long, so completely, that what remains is only ash. Still warm, perhaps, still faintly glowing, but the fire itself is already over. The iron core continues to grow heavier. The pressure of the outer star pressing down on it continues to grow. And then, not with a sound, not with any warning that could be observed from outside, the balance tips. The outward push falls below the threshold that gravity needs, and the core, which has held itself up for all those millions of years, simply stops. What happens next takes less time than a single breath. The collapse of a stellar core is one of those things that the human mind approaches and then quietly steps back from, because the numbers involved are so far outside ordinary experience that they stop meaning anything in the usual sense. So let's not use numbers. Let's just try to feel the shape of it. Imagine something the size of the Earth. Just something the size of the Earth. Just something that large. Now imagine it collapsing, falling inward on itself, in roughly the time it takes to blink. That is what happens to the core of a dying massive star. In a fraction of a second, something Earth-sized is crushed down to something roughly the size of a city, not compressed slightly, not squeezed, crushed, utterly, completely, down to a density that has no comparison in ordinary experience. To try to approach that compression with an image, imagine taking every ocean on Earth, every drop of the Pacific, the Atlantic, the Arctic, all of it, and squeezing it into a swimming pool. Then into a bathtub, then into a thimble. And then, just as you think you've reached the limit of what is possible, squeezing it further still until the water is no longer really water in any ordinary sense, until the very nature of what it is made of has changed. The collapse happens faster than sound could ever travel through the material itself, which means the inner part of the core is already gone, already crushed into something new. Before the outer part even knows anything has happened, there is no signal that could travel fast enough to warn the layers above. They simply continue falling inward, following gravity, until they hit what the core has become. And what the core has become is, by this point, extraordinarily resistant to being compressed further. The newly formed dense object at the center pushes back. The infalling outer layers hit it the way water hits a stone, and they bounce. Not gently. They bounce outward with a force that tears the entire outer star apart, sending its material flying outward across light years of space in the explosion we call a supernova. A supernova is one of the most energetic events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. There is a record from Chinese astronomers in the year 1054 describing a new star appearing so bright it could be seen during the day for weeks. What they were watching was a star dying, a star that had probably been burning since before the first animals walked on land. And the remnant of that explosion is still there today. A slowly expanding cloud of gas and dust in the constellation we call Taurus, with something small and extraordinary still sitting at its center. But the supernova, for all its light, is almost a side effect. The real event is the thing left behind. After the outer star has been flung away, After the light has faded and the gas has dispersed, after all that noise and energy has moved on across the universe, what remains at the center is quiet. A small, dense object, perhaps 20 kilometers across, roughly the distance you might drive to reach the nearest large town, sitting alone in the slowly expanding remnant of what was once a star far larger than our sun. It does not burn. It does not glow, at least not in any way that looks like burning. It simply exists, patient and still, the way a stone at the bottom of a drained lake simply exists. That stone is a neutron star. And to understand what it actually is, what it is made of, what holds it together, why it is the way it is, we need to take a small step back and think about something much smaller. You are made of atoms. Everything around you is made of atoms. The pillow, the air, the walls, the distant stars, all of it, at the smallest scale we can observe, is made of these tiny, ancient structures. And one of the most quietly astonishing things about atoms is how much of them is simply nothing at all. An atom has two parts. At its center is a nucleus, a tiny, extraordinarily dense kernel of matter. And far out around that nucleus, at a distance that is enormous relative to the size of the nucleus itself, electrons drift. Not drift exactly. They move in patterns that are stranger and more interesting than simple orbits. But for the purposes of tonight, think of them as distant companions circling far out in the emptiness around the center. How far out? If you were to blow up a nucleus to the size of a marble, the nearest electron would be circling somewhere around 0.5 kilometer away. Everything between the marble and that distant electron is empty space. The atom is almost entirely nothing. And since everything is made of atoms, everything you have ever touched, every surface that has ever felt solid to you, is almost entirely nothing, held together by invisible forces that create the impression of solidity. The nucleus itself is made of two kinds of particles, protons, each carrying a tiny positive charge, and neutrons, which carry no charge at all. Protons and neutrons are packed together tightly in the nucleus, held by a force that operates only at very short range, but is extraordinarily strong within that range. The number of protons in a nucleus determines what element the atom is. 1 proton means hydrogen, 2 means helium, 26 means iron. The protons and neutrons together determine the atom's weight. Now, hold that picture in mind. The nucleus at the center, the electrons drifting far away, the vast emptiness in between, and imagine what happens when you begin to compress matter with a force beyond anything in ordinary experience. The first thing that happens as pressure increases is that atoms are pushed closer together. The empty space between them shrinks. Then the electrons, which normally occupy their distant orbits with a kind of settled ease, begin to be forced into smaller and smaller spaces. This itself creates a resistance, a push back against the compression, because electrons resist being crowded. But if the pressure is great enough, that resistance is overcome. In a neutron star, the pressure is not merely great enough. It is so far beyond great enough that something remarkable happens. The electrons are not merely crowded, they are forced inward all the way into the nucleus itself. And when an electron reaches a proton inside the nucleus, the two merge. They combine into a neutron and in the process release a tiny, almost massless particle that barely interacts with anything and passes straight through the star and out into space. The proton is gone. The electron is gone. What remains is another neutron. This happens across the entire core, to every atom, all at once. The electrons vanish into the nuclei, the protons are converted. The nuclei themselves dissolve as structures, because without their characteristic number of protons they are no longer distinct elements. They are just neutrons, pressed together with almost no space between them. The architecture of the atom, that ancient, elegant arrangement of nucleus and distant electron, simply ceases to exist. What remains is something that has no real name in everyday language. A sea of neutrons packed together shoulder to shoulder with almost none of the emptiness that defines ordinary matter. The material that was once a stellar core made of atoms like any other matter has become something else entirely. Not a gas, not a liquid, not a solid in any familiar sense. A neutron star. The density of this material is genuinely beyond comparison, but we can try to approach it from one direction. Ordinary matter, rock, metal, water, flesh, is almost entirely empty space, as we said. Neutron star material has had that emptiness removed. All of it, or nearly all. What would fill a teaspoon of this material would, if you could somehow bring it to Earth, weigh roughly as much as every mountain on Earth combined. Not every mountain in one country. Every mountain on the planet. In a teaspoon. And yet the neutron star holds together. It does not simply collapse further under its own weight. Something holds it up. There is a rule written into the nature of matter itself. Not a rule that was decided or agreed upon, but something that simply is as fundamental as anything we know. And it goes something like this. Two identical particles cannot be in exactly the same place at exactly the same time, in exactly the same state. It is not that they resist being in the same place very strongly. It is that it is genuinely, completely not possible. The universe simply does not permit it. This rule applies to neutrons. Pack them together and they resist. Not because they repel each other the way magnets repel, though there are forces involved too, but because of this deeper, stranger prohibition. When you try to squeeze neutrons into the same space, they push back. Not with a force generated by heat or pressure in any ordinary sense, but with something more fundamental than that. It is the fabric of matter itself saying no further. This is the force that holds a neutron star up, not burning, not heat, not any ongoing reaction, just the quiet, immovable resistance of neutrons refusing to be compressed into the same space, the entire weight of a dead star pressing down, and this single rule of nature holding it. It is worth sitting with that for a moment. The neutron star is not doing anything. It is not working to hold itself up the way a living thing works to stay upright. It simply exists in a state where collapse is not permitted. It could, in principle, remain this way for longer than the current age of the universe. Longer than many ages of the universe. There is nothing to run out, no fuel to exhaust. The rule does not weaken with time. The pressure at the center of a neutron star is difficult to approach with everyday language. We can say it is many times higher than the pressure at the center of our sun, but that comparison doesn't help much because the pressure at the center of the sun is already beyond anything experienced on Earth. We can say it is the highest pressure of any known stable object in the universe, and that gets closer to the truth, but still doesn't quite land as a feeling. Perhaps it is enough to simply say, this is where pressure reaches its limit. This is as far as pressure goes before the universe runs out of ways to hold matter together. But a neutron star is not just a uniform ball of compressed neutrons. It has structure, it has layers, and the outermost layer is, in a strange way, the most familiar, because it is the only part of a neutron star where atoms still partially exist. The crust of a neutron star is a rigid crystalline layer, rigid in the way that steel is rigid, but far more so, a material of extraordinary strength capable of holding enormous internal stresses without yielding. The atoms in this crust are not ordinary atoms. The electrons have already been partially stripped away. The nuclei are unusually neutron-rich, but there are still nuclei, still some structure recognizable as atomic. It is a shoreline, in a way, the boundary between the matter we know and the matter we have no everyday name for. Beneath the crust, moving deeper, the neutrons begin to flow. Not flow the way water flows, carrying friction and turbulence. Flow without any friction at all. Every particle moving freely, not losing any energy to its neighbors, not slowing, not stopping, This is a state of matter that has been observed in laboratories, but only at temperatures within a fraction of a degree of absolute zero, the coldest possible temperature, where all ordinary thermal motion stops. The fact that it exists inside a neutron star, which is actually quite hot by most standards, is one of the deep puzzles that keeps researchers returning to these objects. And deeper still, at the very center, where the pressure reaches its absolute peak, the honest answer is that nobody knows for certain what is there. The neutrons themselves may no longer be quite neutrons. The particles that make up a neutron, smaller constituents that are not normally found alone anywhere in the universe, may there be freed from their usual confinement, moving through the core in a state that has never been directly observed and may be fundamentally unobservable from the outside. The mathematics suggests several possibilities. The experiments to distinguish between them are, in many cases, not yet possible. There is something genuinely restful about this if you let it be. The most extreme object in the known universe, the densest stable thing that exists, and at its heart a mystery. Not a mystery that feels like a lack, but one that feels like depth, like looking into very still water and not being able to see the bottom and finding that peaceful rather than troubling. The crust, meanwhile, is doing something interesting. All that rigidity, all that stored stress, occasionally it releases. The crust shifts suddenly and briefly in what is called a starquake, and in those few fractions of a second, a neutron star can release more energy than our sun produces across several years. A pulse of X-rays, a brief brightening, and then the star settles again into its patient stillness. These events have been observed. We have watched neutron stars flinch. Not all neutron stars are quiet. Some of them announce themselves regularly, precisely, across the distance of the galaxy in a way that when it was first heard, nobody knew what to make of it. The year was 1967. A graduate student named Jocelyn Bell Burnell was working at a radio telescope in Cambridge, a large array of antennae spread across several acres of English countryside, designed to pick up radio waves coming from distant objects in the sky. Radio waves are invisible to the eye, but they carry information, and the telescope translated them into traces on a paper chart. Burnell's job, in part, was to go through those charts by hand, looking for interesting signals. The charts were long. The work was patient, detailed, the kind of work that requires a particular quality of attention, not excited attention, but settled, practiced attention. And one day, going through the paper traces, she noticed something that didn't fit. A signal, pulsing, perfectly, precisely, regularly, repeating at an interval so exact that it was unlike anything seen in natural data before. Not approximately regular, not mostly regular, exactly regular, to a degree that the best clocks of the day could barely match. The pulse came every 1.3 seconds, like a heartbeat that never varied by even a fraction. The team was, understandably, uncertain what to think. Natural phenomena in astronomy were known to vary, to flicker, to pulse in rough rhythms, but nothing was known to pulse with this kind of mechanical precision. The signal was given a half-serious designation that has since become famous, LGM-1, Little Green Men. The possibility that it might be artificial, a signal from somewhere else, was considered gently and then set aside as more data came in. More pulsing objects were found. Then more, all of them precise, all of them different. Whatever these were, there were many of them across the sky. What Burnell had found was a pulsar, a neutron star spinning so fast that it sweeps a narrow beam of radio waves around like a lighthouse, and every time that beam crosses the Earth, we receive a pulse. The precision of the timing is a consequence of the neutron star's extraordinary stability. Once spinning, with almost nothing to slow it down and no friction worth speaking of, it keeps time with a steadiness that puts our best mechanical clocks to shame. The reason neutron stars spin so fast goes back to the collapse. When the stellar core fell inward, it was already rotating. All stars rotate, slowly, the way our sun rotates roughly once a month. As the core collapsed, that rotation was preserved, but concentrated into a far smaller space. This is the same principle at work when a figure skater pulls their arms inward during a spin. The rotation speeds up as the spinning object becomes more compact. A core that was rotating once a month, collapsed to a fraction of its original size, might end up rotating dozens of times per second. Some pulsars rotate hundreds of times per second. There are neutron stars that complete more than 700 full rotations in the time it takes you to draw a single breath. The magnetic field of the star is also transformed by the collapse. The original star had a magnetic field. All stars do. And as the core compressed, that field was concentrated in the same way the rotation was, intensified enormously. The magnetic poles of the neutron star, which are not necessarily aligned with its rotational poles, funnel the star's energy into two narrow beams, shooting outward from the magnetic poles like the beams from a lighthouse. Wherever those poles happen to be pointing as the star spins, the beam sweeps the sky. We only detect a pulsar when one of those beams happens to point toward Earth during its sweep, which means that for every pulsar we have found, there are likely many more neutron stars whose beams simply never cross our part of the galaxy. The sky is full of lighthouses we cannot see from where we stand. Bernal herself was not included in the Nobel Prize that was later awarded for the discovery of pulsars, and a mission that has been discussed and debated in the decades since. She has spoken about it with a generosity that says something about her character. The discovery itself stands regardless. A young woman going through paper charts by hand, noticing something that didn't fit and changing our understanding of what the universe contains. Some pulsars slow over time, gradually losing their rotational energy to the beams they emit. Others, in a different class, have been spun back up by drawing material from a companion star orbiting nearby, and these can reach those extraordinary rotation rates of hundreds of times per second. Each one a city-sized object, turning in the dark, patient and precise, sending its signal outward across thousands of light years as if it has something to say. Let us descend, slowly, without hurry, as if we are sinking through still water, down toward the surface of a neutron star, and then through it, layer by layer, into something that becomes progressively stranger the deeper we go. From a distance, a neutron star is almost invisible. It radiates, but not in the wavelengths our eyes were built for. It may emit X-rays, radio waves, gamma rays, forms of light that carry more energy than visible light, or less, but none of them. The warm glow we associate with stars. Up close, the surface would be unlike anything in ordinary experience, smooth beyond anything that exists on Earth, smoother, it has been calculated, than the most perfectly polished ball bearing ever made, by a factor that makes the comparison almost meaningless. The gravity at the surface is so strong that light itself is bent as it leaves, not metaphorically, but actually curved, so that if you were somehow floating near a neutron star, you could see a portion of the far side of the object, wrapped around by gravity into your field of view. The surface, and the crust just below it, is where the atoms still hold some of their structure. We said this before, but it is worth staying with for a moment. These are not ordinary atoms. They are stripped of most or all of their electrons. Their nuclei are heavy with extra neutrons. Their arrangement is crystalline and rigid in a way that has no equivalent in any material on Earth. But there are still nuclei. There is still something we might recognize distantly as atomic structure. This crust is where starquakes originate. The crust stores stress the way a tectonic plate stores stress before an earthquake, slowly, silently, over long periods of time, until the accumulated tension exceeds what the material can hold. And then it shifts. In a fraction of a second, a portion of the crust readjusts, and the energy released in that moment is extraordinary. In the year 2004, an event was detected from a neutron star roughly 50,000 light-years away. a burst of energy so intense that even at that distance it briefly affected the upper atmosphere of Earth, disturbing the layer that reflects radio signals. A dead star, half the galaxy away, flinching, and the echo of that flinch reaching us here. Below the crust, the neutrons begin to flow. The transition is not sharp. There is a region where the crystal structure of the crust gives way gradually, the nuclei becoming less and less distinct, until what was a rigid solid becomes something more like a fluid, but unlike any fluid you have encountered. This fluid flows without resistance. Every neutron moves freely, without losing energy to friction, without slowing. A current started in this fluid would, in principle, continue forever without any push to maintain it. This state of matter has a name in physics, but the name matters less than the image. It is matter that has, in a sense, lost all internal resistance. It moves as one. A current in this fluid would carry not just movement, but also a kind of magnetic effect, and this may be part of what maintains the extraordinary magnetic fields of neutron stars over long timescales. The fluid interior and the magnetic field are coupled in ways that researchers are still working to understand. Deeper still, the density increases, the neutrons are packed ever more tightly. And here, in the innermost regions of a neutron star, the honest position of science is one of genuine uncertainty. Not the uncertainty that comes from incomplete measurement, but something more fundamental. The uncertainty that comes from being at the edge of what our current understanding of matter is built to describe. Neutrons are not, themselves, the smallest things. Each neutron is made of smaller constituents, 3 of them, bound together by a force so strong that under ordinary circumstances they are never found apart. In the deepest interior of a neutron star, the pressure may be sufficient to break that bond, to free those smaller pieces from each other, creating a state of matter in which they move freely rather than being locked into neutrons. This has never been directly observed. It may not be observable from outside the star at all. The equations that describe it are complex and contested. Different researchers, using different but equally valid approaches, arrive at different answers. And there may be other possibilities. There are particles that exist briefly in high-energy experiments, cousins of the neutron, heavier and unstable under ordinary conditions, that might, under sufficient pressure, become stable and appear in the deep interior. There may be forms of matter in the core of a neutron star that have no representation anywhere else in the universe. We do not know, and that not knowing is not a failure. It is a frontier. There is something deeply human about standing at the edge of what is understood and simply looking with curiosity and without anxiety into the depth beyond. The neutron star holds all of this: the rigid crust, the frictionless interior, the uncertain deep, in a sphere roughly the size of a city, quietly in the dark. Some neutron stars are not alone. In the same way that many ordinary stars exist in pairs, orbiting each other in long, slow gravitational dances, some neutron stars have companions, and when that companion is another neutron star, something remarkable begins, slowly, over millions of years. 2 neutron stars in orbit around each other are not a stable arrangement, not in the very long run. As they orbit, they disturb the fabric of space around them, sending out ripples the way a stone dropped in still water sends rings outward. These ripples carry energy away from the system, very slowly, very gently, and as energy is lost, the orbit shrinks. Gradually, over millions of years, the 2 stars spiral closer. The spiral is patient. There is no rush in it. 2 dead stars, each the remnant of something that burned for millions of years, circling each other in the dark, growing slowly, imperceptibly closer, decade by decade, century by century. The story of how we first understood this spiral is worth telling. In 1974, 2 astronomers studying pulsar signals noticed something unusual about one particular pulsar. Its timing was drifting in a pattern that suggested it was in orbit around something, the pulse arriving slightly earlier when the pulsar was on the near side of its orbit, slightly later when it was on the far side, because the signal had a shorter or longer distance to travel. And as they tracked the timing over years, they found that the orbit was shrinking, slowly, precisely, in exactly the amount predicted if the two stars were losing energy to those space. It was the first indirect evidence that such ripples were real. The two astronomers were awarded a Nobel Prize for this work in 1993. But the ripples themselves, the actual physical disturbance in the fabric of space, had never been directly detected. Detecting them requires an instrument of almost incomprehensible sensitivity. The ripples stretch and compress space as they pass, but by the time they reach Earth from any reasonable distance, the stretching is fantastically small. The entire distance between the Earth and the nearest star might be stretched by less than the width of a human hair. To detect a ripple from a more distant event, you need to measure a change smaller than the width of a single proton, across a distance of several kilometers. This was achieved for the first time in 2015, when a pair of instruments in the United States, long tunnels, kilometers in length, with mirrors at each end and lasers bouncing between them, detected a ripple from two merging black holes. The instruments were sensitive enough to measure that almost unimaginably small change in length. The technology required decades to develop. And then, in August of 2017, the same instruments detected a different kind of ripple. This one was accompanied by light, by a burst of gamma rays, by a glow that telescopes around the world and in orbit rushed to observe. The ripple was from two neutron stars, roughly 130 million light-years away, completing their long spiral and finally meeting. The merger lasted a fraction of a second. Two neutron stars, each carrying more mass than our Sun, each the size of a city, colliding at a significant fraction of the speed of light. The energy released in that collision was, briefly, extraordinary. And in the conditions of that collision, in the heat and pressure and chaos of two neutron stars becoming one, something was created. Gold? Not a small amount of gold, more gold than exists in the entire Earth, a quantity of gold and silver and platinum and other heavy elements forged in the seconds of the collision and flung outward into space, the way all the material of a supernova is flung outward, to drift through the galaxy and eventually become part of new stars, new planets, new things. The gold in any ring you might be wearing, the gold in any piece of jewelry anywhere on Earth, was very likely forged in an event like this one. Two neutron stars, spiraling together over millions of years, meeting in a fraction of a second, and in that meeting producing the heavy elements that seeded the cloud of gas and dust that eventually became our solar system. There is something very quiet in that, if you let it settle into you. The ring on a finger, the necklace in a drawer, the coin in a pocket, all of it born in a collision of dead stars, carried across 100 million light-years and billions of years of time to end up here, in a room, near a hand that is growing heavy with sleep. The ripple from that collision, that gentle stretching and compressing of space, passed through the Earth in 2017 and was felt by those extraordinarily sensitive instruments, and then continued outward, growing fainter, spreading across the universe like all the other ripples from all the other collisions that have happened across all of time, crossing distances that have no everyday meaning. The two neutron stars are gone now, merged into something else, still sitting in that distant galaxy, still quiet, still dense, still holding whatever secrets its interior contains. The gold they made is scattered across space. Some of it, eventually, came here. We have come a long way tonight, not in any hurried sense, more the way a slow walk covers ground without you noticing until you look up and find yourself somewhere unexpected. We began with a star, enormous, burning, balanced between the outward push of its own fire and the inward pull of its own weight. We watched it exhaust the last of what it had to give. We felt the core surrender quietly in the space of a breath. We fell inward with the collapsing layers, felt the bounce, watched the outer star fly apart in light, and we found, in the quiet aftermath, a small, dense remnant, a neutron star, sitting alone, patient, made of matter pressed into a form that has no parallel in ordinary experience. We learned what atoms are. Those ancient, mostly empty structures, nucleus at the center, electrons drifting far away. And we saw what happens when the emptiness is removed, when the electrons are forced into the nucleus, when protons become neutrons and the atom as a structure ceases to exist. We found a sea of pure neutrons, held together by a rule so fundamental that the universe itself enforces it. No two of them can be in exactly the same place at the same time. That rule, and nothing else, holds the neutron star up. We walked through the layers, the rigid crystalline crust capable of storing years of solar energy and releasing it in a moment, the frictionless interior flowing without resistance, and the deep center where our understanding softens and the honest answer is that we are not sure. We found pulsars spinning hundreds of times a second, sweeping their beams across the galaxy, discovered by a young woman going through paper charts in Cambridge. We found 2 neutron stars spiraling together over millions of years, colliding in a fraction of a second and producing in that collision the gold that eventually found its way into the world you live in. Now we reach the edge. A neutron star is held up by that fundamental resistance of neutrons to being compressed. But there is a limit. Add enough mass to a neutron star, through a merger or by drawing material from a companion star over long periods of time, and the weight pressing down eventually overcomes even that resistance. The rule does not break. But the star grows heavy enough that gravity wins anyway, and the collapse begins again. This time, there is nothing to stop it. The neutrons cannot resist further. The collapse continues, past any state of matter we have a name for, past any density our equations can describe with confidence, into something from which nothing, not matter, not light, not any signal of any kind, can escape. The space around the collapsing object closes over, the way water closes over something dropped into a still pool, and what remains is a region of space from which there is no return. We do not know what is inside. We do not know if the question of what is inside is even a question that has a meaningful answer, given our current understanding of how space and time behave in such extreme conditions. The mathematics suggests that the collapse continues indefinitely, but the mathematics may be incomplete. This is one of the deepest open questions in all of physics. What actually happens at the center? What matter becomes when it is compressed beyond the point where any known rule can hold it? The neutron star, then, is the last stable resting place, the most compressed, most dense object that can still be called an object, that still has an inside and an outside, that still holds its shape, that still obeys rules we can write down and study. Beyond it is the threshold, and the threshold is where the story, for now, ends. But let us not end there. Let us come back to the neutron star itself and simply rest with it for a moment. 20 kilometers across, perhaps a little more, perhaps a little less. We are not entirely certain, because measuring the size of an object that small at that distance is genuinely difficult. Heavier than our sun, which is 1,000,000 times the size of the Earth, spinning, perhaps slowly, perhaps hundreds of times a second, covered in a crust of strange, rigid matter, crystalline and ancient. Inside, neutrons flowing without friction through the deep interior. At the very center, something we have not yet understood. It does not burn. It does not breathe. It does not change in any significant way over timescales that dwarf the history of life on Earth. It simply is, the way a stone simply is. Except that this stone is made of matter pressed into its quietest, most concentrated form, the endpoint of a journey that began with a star far larger than our sun, billions of years ago, in some distant part of the galaxy. And it is made of neutrons, particles. The same kind of particles that are inside every nucleus of every atom in your body right now. Not different particles, not exotic or alien things. The same ones, just pressed together with the emptiness removed in a sphere the size of a city somewhere in the dark. There is something quietly comforting in that, if you are willing to receive it. The universe is strange, yes. It contains objects beyond ordinary imagination, pressures beyond any comparison, densities that make the word solid feel almost meaningless. A neutron star is not something foreign to you. It is matter, like you are matter, ancient, patient, quiet matter, compressed to its most essential form. The campfire burned for millions of years. The ash collapsed. The stones settled at the bottom of the drained lake. And now it turns slowly in the vast dark. A lighthouse that has been spinning since before the earth existed, sending its signal across distances we have no words for. Patient as only something truly old can be patient. You are made of the same material, arranged differently, given different rules to follow, at lower pressures, in a warmer, gentler place, but the same. Let that be the last thought of tonight, if it arrives gently enough. Not a thought to hold on to, just one to let drift through, like light through a curtain, and then go. The day is already far behind you. The body is already heavy, already settling. The mind can let go of whatever it was carrying, just for now, just for the hours ahead. Somewhere out there, a neutron star is turning. It has been turning for longer than you can imagine, and it will continue long after anything on Earth has changed beyond recognition, unhurried, still, doing nothing but existing, in the dark, in the quiet, in the vast and patient universe. Drift now, if you're ready. Sleep well.